brushless DC motors. And you'll see that the topology is actually quite different from brush DC motor in the sense that the coils are now actually on the stator and the permanent magnet is on the rotor. So it's like we took our brush DC motor and flipped it inside out to create this topology. Now what I'm going to do is I'm going to pass some current through this coil in such a way that it creates a north pole in the air gap on the top stator piece, and it'll create a south pole in the air gap on the bottom stator piece. Now I'm going to put a hand crank on this motor, and I'm going to essentially rotate it through 360 degrees, as you can see here. And what I'm doing is I'm plotting the torque that the motor is generating as it's rotating. Now I will tell you that I've never seen a motor that had this beautiful of a torque waveform, and it's almost impossible to achieve because you would have to have uniform flux density in the air gap in order to get that kind of performance, and no motor can achieve. So to get around this undeterministic nature in terms of which direction the motor will want to spin, the solution is we add more phases to the stator. So in this case right here, I'm going to turn on some current in phase A, and when I put a rotor inside that stator structure, it's going to line up in the direction as shown here. Now what do you suppose I would have to do in order to get the motor to spin in a clockwise direction? Well, the answer is I would want to take the current out of phase A and put it into phase C. In particular, in this case, it would be negative current into phase C, and that will cause the rotor to now try to line up with the phase C stator pole. Now this process of taking the current out of one coil and putting it in another coil, it has a specific name in motor control. It's called commutation. And basically, commutation means taking the current out of one circuit and putting it into another circuit. So in this case, I've taken the current out of coil A, I've put it in coil C, and the rotor now wants to align with the stator poles of coil C. And I can continue this commutation process and make the motor continue to spin around following the rotating magnetic field of the stator as shown in this diagram. However, this is not a very efficient way to control the brushless DC motor. In fact, if you look, I'm only controlling one stator phase at any given time. And that means that 2 out of the 3 coils are not being used for anything. There's actually a better way to do it, and let's take a look at that in the next slide. So here I have my 3-phase stator arrangement with the rotor inside of it. And what I'd like to do is to come up with a procedure by which I can drive multiple coils to generate positive or negative torque. So the way I'm going to do this is I'm going to put positive current into all 3 phases of the motor at the same time. And then once again, I'm going to put like a hand crank on the motor, and I'm going to spin it, I'm going to rotate it very gently through 360 degrees. Now the torque waveform that you see for phase A, that's the same one that we saw in the first slide when we talked about brushless DC motors. But what you'll notice is that the torque waveforms for phase B and phase C are identical to this. The only difference is they're separated in phase by 120 degrees, and that's because the B and C coils are separated from phase A spatially by 120 degrees. So we end up with torque waveforms that look like this. Now, by looking at each one of those commutation intervals, here's the rule that I'm going to apply. If positive current in a particular coil for that commutation interval will result in positive torque, and implement that in some kind of controller, whether it be some logic gates or a microcontroller, microprocessor, there's lots of different ways to do that. But there's just one catch to this whole process, and that is, in order for me to know which transistors I should turn on or turn off, I need to know where the rotor position is. So that's why I have this Hall effect arrangement on the back end of the motor. There's a little magnetic disc. In this case, it's got 4 pole pieces on it, and I've got 3 Hall effect sensors separated from each other by 120 degrees. Now these are digital Hall effect sensors, which means they don't really detect the absolute analog field strength of the little magnetic disc. All it's detecting is when I transition from a north pole to a south pole and vice versa. Brushless DC motor, which actually consists of 12 stator poles. And this is still a 3-phase motor, but those 3 phases are split among 12 stator poles. Here's a picture of a rather interesting motor which I have in my lab. And you can see it's a 3-phase machine, but it does consist of 12 stator poles, just like we talked about in the previous slide. And it's a 4-pole rotor. You can actually see some of them here, some of them, like I said, So this is just like the topology that we talked about in the previous slide, with one exception, and that is this is a cup design, so the rotor is actually spinning on the outside of the stator pole pieces. Now there's several reasons why you might want to do this. One advantage with this topology is that as the motor goes faster and faster, you don't have to worry about the magnets flying off the rotor and expanding into your air gap. In this case, what it does, if anything, is it actually makes your air gap a little bit bigger as the rotor pieces by centrifugal force are pressed against the outside of the shaft.